look at some of the secondary effects that kind of make the orbit of the satellite non-ideal. These are the things that are very present in mission planning and very present when you operate the satellite. We cannot really address them to the full extent in this course because the things get overly complicated. But I would like to do is just go through them so that you're aware of what is going on, and then we're going to do a few examples about some of the things that you've seen before. So let's talk about orbital perturbations, how you launch this. It's just a nice story, but you need to be kind of aware of some of these things. So what do we refer to when we say orbital perturbations? Well, these are the difference between the actual orbit and the one that you obtain by using Keplerian or Newton's laws of motion. Now, you've seen in the notes and from our discussion thus far that the Kepler laws are a kind of solution to the ideal situation when you have Earth, which is an ideal big mass, and then small mass of a satellite. There are other things that are in between those two that affect the motion of the satellite, and they cause this orbit to not be pure ellipse or to kind of precess over time or change over time. There are some the major sources of these perturbations are listed here. The first one is because the Earth is non-ideal, and I'm going to talk about what are the things that makes Earth non-ideal. Then the fact that Earth is not the only mass around. There's moon, there's sun, and there's pull from pull from those two that change the orbit of the satellite, especially if the satellite is in a geostationary orbit because it's relatively far away from the Earth. There's atmospheric drag that affects the satellites that are in the low orbit because the atmosphere doesn't just stop. It kind of gets less dense. And what we're going to I'll show you how this is taken into account and where in the two-line element data you will find the description of what the drag is on the particular satellite. And then the sun is the big guy on the block, and it dominates everything that happens around us. So there is something called solar radiation and solar wind that I'm going to briefly mention and at least explain so that you know what we are dealing with. What happens is the way how we model this is we always start. This is a general case in engineering. What you do is you, especially when you try to model real work, what you do is you model the big chunk of it, right? And we've done that, for example, in auto propagation. Let's say, let's model the long distance part and then add all the secondary effects on the top of it. Here, what we're doing, we're saying, well, it has to be close to Keplerian orbit, and then there are secondary variations that we're going to model on the top of it. And what we do is we find what is called osculating orbit or Keplerian orbit at some time, and then assume that, that Keplerian orbit, as you have seen, is characterized with 6 different parameters. Right? We can pick them somewhat arbitrary. And we discussed the last time what are the ones that we pick in the book and what are the ones that are in the two-line element data. And then what you do is you say, okay, well, these are the parameters at this time, and then they vary slowly over time, and then you model these variations. And this is kind of approach how we can model every function. You model it through its Taylor series, which is this kind of approach. And then what we do is, on the top of it, we do the measurements that help us calibrate from time to time. So we never let the satellite just without any feedback. You kind of predict where it's going to be, and then you measure, and then you re-predict and measure, and then over time you detect if it's drifting. And then what happens in real practice, we have to make sure that operationally we keep the satellites where they're supposed to be. And we'll talk about in chapter 3, how do you move them around and what are the things that we have at our disposal to make sure that they stick to the position in the orbit that they're supposed to be in. So, what are the effects of the non-ideal Earth? Well, once when you look at it from the far, Earth is a sphere, but when you come up closer, then you'll notice that there are quite a few non-ideal things. First, the Earth is not a sphere. Earth is, it has a belly, right? It has a bulge at the equator, so it's much wider this way than this way. Not much wider, somewhat wider this way than this way. You can see that there's a 32 kilometers difference. That is not much of a difference, and that's why these equations that we use so far make a lot of sense. But if you have to put something in space and that stays there for 15 years, even the minute differences accumulate over large periods of time. That's why this is important to take into account. Also, what happens is Earth is not uniform. There are different materials that it is made of, and what that does, it kind of makes distribution of the mass in this sphere non-uniform. And what that does, it changes the gravitational field. Because if you think about what we learn in physics, you can say that the gravitational field of the Earth is the superposition of all the elemental mass elements. And if these mass elements are not uniformly distributed, you end up with a gravitational field that's not uniform as well. In a first order approximation, it is what we did in lecture 2, but when you start looking closer, then you have non-ideal gravitational field. And hope of modeling that gravitational field is to a great accuracy, by just looking at the Earth itself. It's not really something we can do. So what we have done in the past, and there's just a mission I think that terminated last year, where we send a special kinds of satellites whose purpose is to do nothing but to measure the gravitational field of the Earth. And what they do is they fly around the globe and then come back with very precise maps of what the gravitational field looks like. So in that case, you actually make that part of the model, and when you plan the missions, you can actually work with the measured data and have a much better idea how the satellite move in the orbit. Why is all of this important? Just a preview of what is coming. When you launch the satellite, it needs to follow the orbit. The system is designed so that it is in a particular point in space at a given time. All of these secondary effects will act so that the satellite is not there where it's supposed to be. And what you need to do to make everything operational, you have to move the satellite to a proper location. The way how you move the satellite, you have to turn up the engines on a satellite, turn on the rockets or whatever motors you have out there, and actually move it to where it's supposed to be. When you do that, you're burning the fuel. And that has two implications. First, you have to take a lot of fuel with you to be able to do these maneuvers over the period of 15, 20 years. And second is, once that fuel is gone, the satellite is gone as well. You cannot leave it there because it will drift out of the orbit and potentially interfere with other satellites. So what we are, the position that we are in right now is that most of the telecom equipment that we launch will survive for the duration of 15 years and more. And most of the time when the satellite is decommissioned, it is not because the electronics stopped working, but you simply ran out of fuel. And you have no way of maneuvering the equipment, so you either put it in a dead orbit or you kind of burn it down to the ground. Okay, so, because the mass is not uniform, what happens as a result of this non-uniform distribution, we have, if you look at just geostationary orbit, we have 4 interesting points. There are 4 equilibrium points. Two of them are stable equilibrium points. They're at 75 east and 252 east. What that means is, if you look at if you leave the satellite in a geostationary orbit and you just don't do anything to correct its path, over time, all of the satellite will collapse in one of those 2 locations, right? Those are the locations of the stable equilibrium. They keep on drifting until they fall there. And that's where at 75 east and 252 east, if you move either east or west, your potential energy grows. So you're kind of in a valley there of the gravitational field. And we have 2 unstable equilibrium points, 162 and 348. So if you were to launch the satellite, the best point to put it is here, because you can operate for the longest time. It is naturally drifting towards this point. For all the other locations over time, you have to burn the fuel and to maintain them within a half a degree box that they're supposed to be. So that's the Earth itself. Now, if you look at the way how things are more globally, then you realize that that Earth is not the only mass that acts upon a satellite. If this is kind of schematic, obviously it is not drawn to scale. This is over there in Orlando, but it shows you that you know, you have Earth, you have a pull of the moon, and you have a pull of the sun. And even though these are relatively small, over extended period of time, they will accumulate. This is one of these gravitation forces tend to move satellite out of the orbit. This is for the, so under these conditions, under the influence of these things, the orbit will precess up to 1 degree per year. So the location of the satellite would change, and you would have to take it into account. And we, as I said, we have to burn the fuel to get those into account. And as I said, that all the calculations are always measured and reported in TLE data for all the satellites. Atmospheric drag for the, I have decided to put the slide on this one because if you look at the TLE data, this one is explicitly modeled, and if you look at the two lines that we obtained for International Space Station, you have there, you may wonder why is there a first derivative of the mean motion. Well, it turns out that because International Space Station is quite low, you know, at a quite low altitude, it is at the edge of the atmosphere, so there is some drag from the atmosphere itself. And what drag does, you know, as you keep on going around the globe, it actually takes some energy, and as a result of that, your semi-major axis or your altitude starts decreasing, right? And if you leave it like that for a long time, eventually International Space Station will fall onto the ground. Right? So every now and then you have to kind of compensate for that and fly a little bit further away from the, you know, from its current orbit. The approximative equation that allows you to model that is this one here, that tells you that the semi-major axis of the orbit changes as a0 plus 1 plus n0 prime. This is the first order derivative of mean motion, and n0 is the mean motion in revolutions per day, and then t and t0. T0 is the time when you go through T0 is the time at which you have had this particular A0. So if you now, there's a spreadsheet that I'm going to post on a website that will allow you to just plug in the TLE data and see how does the semi-major axis change based on the parameters in the TLE data. This is an example for International Space Station. If you remember last time, we had that International Space Station has 1572 revolutions per day, so that's about 90 minutes of the period. The mean motion divided by 2 is this, so if you do the calculation, you can see that that the changes are relatively small, but nevertheless, you know, if you operate it for several years, over time you need to compensate for the thing slowly falling to the ground. Okay, so how is this dealt with in practice? There are folks out there, scientists, very bright people. They do nothing but kind of model this whole thing, and the result of these models is something that we call Propagators. Propagators is a software that models the motion of the satellites around the globe. There are 3 types of the propagators that we find, and they're kind of listed here in an increasing degree of complexity. First ones are what we call analytic propagators. And these are the ones that make an attempt to model everything using physics, just pure equations and equations of motion, gravity, and so on. The two-body propagator that is the one that we dealt so far. That's the one that assumes that there's just an Earth and a satellite. Now, if you J2 and J4 take into account some additional elements, J2 models the Earth oblateness, solar and lunar gravitational forces, so it is a little bit more complex, but still it makes an attempt to model everything analytically, you know, and so on, right? The one that is one of the most popular is this SGP4. This is the one that is used in the satellite toolkit, which is the one that one of the software packages that is widely used for in the satellite industry. Now, the next one that we have are what is called semi-analytic ones. They actually start from analytic models, and then what they do is they add either integrate measure data or you know, do some additional, usually non-standard things, but whatever they find that it works. They're relatively accurate, as it says here. They can be accurate over many months. These guys, you know, you would, I guess, calibrate them initially with TLE data, and then they will allow you to predict a few days, you know, and then after that you will have to get the new TLE measurements and compensate for these models drifting away from the actual position of the satellite. These guys hold on more. And then there are very precise ones that are kind of solving complex sets of differential equations. These are the guys that actually have that are used by NASA and where you have very, I guess, good computational speed and not so much restrictions in terms of the time, how long does it take. But you will find all of these, and if you have time, do some Googling. NASA has, I forgot what it's named, but it has a MATLAB-based propagator that will allow you to, I know you guys use all MATLAB, so you can get that one for free, and it will allow you to take the TLE data and then use these MATLAB M files to predict the position of the satellite. It comes with a whole bunch of M files, and it comes with plotting routines that will plot everything and show you everything in a 3D. Okay, so how do we launch satellites? Satellites are, I guess, launching of a satellite is a relatively expensive business. You know, I think your books gives us, if memory serves me right, it says it takes about $30,000 to send half a pound of mass into space, right? So it's a pretty expensive endeavor. And the launch itself is expensive. The insurance on the launch is expensive. You don't want to go without insurance, because if something goes, somebody needs to pay off for that. And then very often, even the cancellation of the launch is expensive, because you go through all of these processes, and then here at the Cape, you know, the lightning strikes, and you may scrap the whole launch because you need to go and retest all the electronics, not knowing if the lightning did something to them. So it's a relatively expensive business at this time. But as far as I guess maturity of the technology is very mature. I mean, we have I would say 30, 40 years of launching satellites, and they're kind of launched almost on a daily basis. There are three types of vehicles that actually two types of vehicles that we use to launch the satellites. They're kind of divided here as what is called expendable and reusable vehicles. Expendable vehicles are your rockets, and you kind of put a satellite in a third stage of the rocket. You launch the rocket, and over time, you know, you kind of lose the whole rocket, but the satellite is there. They are the most, thus far, the most popular way of launching the satellites, because it turns out that if you try to return back things from space, it comes really battered and damaged, and by the time you refurbish it, you might as well, you know, went with a cheaper vehicle. And there are three big types of rockets that we use. Ariane is European. Then there's actually Atlas and Delta. These are the U.S. rockets, and then Soyuz. This is a Russian rocket that are used for the launch of the satellite. All of them were developed as a part of the governmental programs, but they're also used to launch the commercial satellite at suitable fee. Now, outside of the rockets, there are reusable launch vehicles, and up to 2011, we had Space Shuttle. There is something called Dragon and Falcon 9. I don't particularly know much details about them. They're operated by SpaceX. SpaceX is a commercial entity, commercial company that is solely dedicated to the space industry. They're actually operating here out of the Kennedy Space Center, and they launch. I mean, if you follow the news, there's quite frequently announcements of the launches. The launch is done in several stages. There are actually at least 3 stages. In the first stage, you want to get out of the atmosphere as fast as you can, and that means that the majority of time when you launch, you go straight up, right? Because think about what is the purpose of the launch, and the best way to explain it is think about throwing a stone, right? You want to throw the stone, but you want it, and the stone kind of follows, falls on the ground, right? But you want to throw it as fast so that as it follows to the ground curves as well. So it kind of goes around the Earth, right? So ultimately, all of these orbits are kind of going around the Earth. But to launch to the orbit, you first go straight up to go through the atmosphere, because that's through the shortest spot, because that's the portion of your launch where the drag is the largest and where you burn the most fuel. And then the second thing you do is you place usually your satellite or launching vehicle in 1 or 2 transitional orbits, and then you manipulate the periges and at what point you kick in the engines so that you eventually position the satellite in the final orbit. I have some descriptions of the launching procedures on the following slides, but the speeds that you need to get so that you can launch something from the Earth are pretty fast. I mean, you have to go, or at least to what we are used to, just walking on the Earth. I mean, in order to launch the satellite in a LEO orbit, so that it's not falling to the ground, you have to move it 7.5 kilometers per second. So that means that satellite in 10 seconds is in Orlando, right? So it's moving quite fast. Also, this is what you see here. I tried to assemble a list of some of the most popular sites where you launch, and you can see that. I mean, they are listed here, but not all of them are used to the same capacity. What we do is usually the most heavily used are the launch sites that are close to equator. And the reason why you go close to equator is because you're saving fuel, right? First, you're actually able to use the rotation of the Earth to propel it, right? So you always launch so that the Earth rotation gives you initial boost. In the U.S., I guess we launch mostly from Kennedy Space Center. In Europeans, they launch mostly from French Guiana, which is a small country on the same latitude as Florida, but on the south side. And then Russians, they all launch from Kazakhstan. You can see other countries where they have launching sites. So this is what I was talking about. There are 2 examples here. First example is when you launch in a single elliptical orbit. So let's say you start from here. You bring the satellite at a relatively small altitude, but you give it enough speed. So what happens is you place it in this highly elliptical orbit where your perigee is somewhere here, and then you let it ride until it reaches its apogee on the other end. And that's where you kick in the additional boost from your rocky motors, and that's where you put it in this higher orbit. What you need to understand is if you take a satellite and you put it in a point in space and you give it a certain velocity, that determines the trajectory that it's going to continue moving on, right? So if I take a satellite, say you're at this altitude and you have this velocity, that automatically results in a given ellipse that it's going to be moving on. So what you do is you plan your launch so that at this point in space you're going to be at this height and a given velocity. This point you turn off the engines and let the satellite ride. And usually you let it ride maybe 1 or 2 times in this orbit. And then when the time is right, then you kick in additional boost and you put it in a geostationary orbit. So that's one way of the orbit. You have the initial stage where you blow through the atmosphere. You have your transfer orbit, and then you have your final orbit. Now, if you launch from the equator, let's say when you do the geostationary launch, then your orbit is the same as is within the equatorial plane. If you launch from other locations, you can only put a satellite in inclined orbits, so there will be another move that will actually move the satellite, move the inclination. This is a similar launch, but here we have 2 transitional or transfer orbits. You launch a satellite in a low Earth orbit, which is usually with a small eccentricity. Then here you add additional velocity to put it in this transfer orbit, and when you get here, you add additional boost to the satellite to put it in the final orbit. Other launches, as it says here, possible. The planning of this is separate from this issue, and needs to go to detail analysis. So this is just I stripped this from some other book, not the one that you're using. They had these nice diagrams that tells you how you actually launch from these 2 locations. As I said, Europeans are launching mostly from French Guiana, and this is a typical launch from there. So they have 4 stages. First stage is injection in the transfer orbit. That's a low. That's elliptical orbit, but it's a low Earth orbit. Then when you get to the apogee, then you transfer into the orbit number 2. Okay, so this is the first stage, is going through the atmosphere into the transitional orbit. Stage 2 is in this orbit. Then stage 3 is going into another one, and then stage 4 is just to make it fast, bring it back into the equatorial plane so that it is a geostationary satellite. Now, French Guiana is closer to the equator than Florida, so therefore this angle that you need to correct is somewhat small. And then this is a launch, typical launch from the Cape Canaveral to Kennedy Space Center. You go from in stage 1, you put in the parking orbit, and you kick at the perigee transfer orbit, another one, and then finally you put it into equatorial plane. All of these launches are showing you the launch of the geostationary satellite, which for communication purposes, they are a vast majority of the satellite. If you're launching in a highly inclined orbit, or those satellites that go around the pole, which are usually remote sensing satellites, they have their own ways of designing the launch. But kind of you use the gravity of the Earth and Kepler's law and just fields that exist to help you in launching. I have listed here some important orbital effects that you need to be aware. I've listed 3 of them. One is the Doppler shift, solar eclipse, and sun transit outage. All of them are important, and they happen as a part of the regular satellite operation. So let's kind of go through that and describe what they mean. Doppler shift is a phenomenon that you are, I assume, familiar. It's the phenomenon that if you have the transmitter that's moving relative to the receiver, then the motion results in a shift of the carrier frequency. If you're moving so that the distance is getting closer, the frequency increases, the wavelength becomes smaller. If you're moving away between transmitter and receiver, the frequency decreases or the wavelength becomes larger. The change in frequency is delta F over Ft. Ft is the transmit frequency, is the carrier frequency that you're operating. Delta F is the change in the frequency, is equal to Vt over C. Vt is the velocity between cell light and the ground point, or between transmitter and receiver. Now, in general, they don't have to be moving straight towards one another, right? They can be moving in any arbitrary way, but then you can decompose the velocity into two components, one that's parallel and one that is going between them, right? And then the component that goes into this equation is the one that is the velocity between. As a result of that, what happens, since our goal is to communicate, as a result of that, you have to have a mechanism of compensating for that, right? Imagine you're supposed to be receiving on this frequency, and that this frequency starts shifting as the satellite is coming towards you, and then as it passes the antenna, then it starts shifting again and around, right? And we can calculate how large that shift can be. For satellites that are in a low orbit, that shift is significant because they're moving relatively fast. And you have to have electronics that captures that. Usually they're called phase lock loops, and they do the compensation. I'll skip this example now. After we go through slides, then I'll go through several examples and work them out in manual. But you have it in the slide. It helps you kind of calculate or get an idea of how large the shift is of the frequency. What is a solar eclipse? Once you place the satellite in the orbit, then the only source of energy outside of the fuel that it carries, but the fuel is remember, is used to maneuver the satellite. So to operate satellite needs to have energy, and you've seen on all the images of satellite there are these huge solar panels that are either kind of like a solar wings, or the whole satellite might be enwrapped in solar cells. So that harvest the sun light to store to generate electric energy that powers all the systems of the satellite. Right, so all the telecom equipment, all the systems for cooling and heating and whatever needs to be done on the satellite outside of maneuvering are using the energy that the satellite harvests from the sun through the solar panels. Now, as you can see from this drawing, if you have a satellite that's moving around the Earth, it is conceivable that at some point in time the Earth is going to be in between the satellite and the sun. And what that means is that the satellite now gets away from its only source of power, and in those instances it has to rely on whatever power it has. And usually the way it works is you have batteries that are on board of the satellite that will store some energy for the duration when the satellite is in an eclipse. But often, if this, depending on how long you're in eclipse, you may actually go to a reduced mode of operation where you shut off some transponders or operate with limited capacity so that you don't lose connectivity to satellite, and still have some energy that allows you to operate. If you look at geostationary satellites, then we here kind of limit, for any arbitrary orbit, this may happen or this may not happen, or this may happen at different times or different duration. But if you look at geostationary satellites alone, this is the profile of how long these durations of the eclipses are. They occur, the longest eclipses are on what is called equinox days. These are the days where we transition from spring to summer and then back from summer to fall. March 21st and September 23rd nominally. And that's where the eclipse may last up to 72 minutes. So 1 hour, a little bit over 1 hour, you're going to be in the shadow of the Earth. And then if you move 23 days before and 23 days after, then you can have, you can see the duration of the eclipse diminished. So for example, 15 days after, you're only 15 minutes or so. Right? There's this graph that I took from your book. And what needs to happen, as I said, when you are eclipsed, you're having a reduced or no power being generated, so you have to rely on your batteries. You can shut off some of your transporters, or you can actually reroute some of the traffic, operate in diminishing capacity when it comes to the communication satellite. These are relatively dangerous because, remember, space is a relatively hostile environment. The temperature there is very close to absolute zero. And when you're not exposed to the sun. And when you're exposed to the sun, it can heat up to a very high degrees. So there are very sophisticated systems that operate on board of the satellite that maintain the temperature and maintain the temperature and maintain the environment so that all the equipment is operating properly. Without energy that we harvest from sun, those systems are also subject to stress. And what happens is when you get in and out of these eclipses, the system is stressed and something may fail. So that's why they're kind of important to design. Now, sun transit outage. Sun is a huge source of electromagnetic radiation. Our RF waves are nothing but electromagnetic radiation. So, but our satellites transmit at the ERPs, let's say 100, 200 watts. Sun transmits at a much, much higher energy. So if your satellite happens to be in the main beam of your receive antenna, but the sun also happens to be within the main beam, chances are the radiation from the sun will block will mask the satellite. The best way to see that is to understand what the noise temperature of the sun is. Remember, the power spectral density of the thermal noise is K times T, right? And then the amount of noise that exists in a given bandwidth is KTB, right? K is constant, B is whatever we have is operating bandwidth, but T is the temperature of what you're looking, right? And if you're looking at the night sky, and in particular if you're looking at a portion of the night sky where there are no close stars, then your temperature is relatively low. It can be as low as just a few kelvins, right? And then compare that against the situation. So that establishes your background. And if your satellite is against the background, with 100, 200 watts, you can reach vast distances and still have a good signal-to-noise ratio. The signal-to-noise ratio is how strong is your signal and how strong is your noise. If you're looking at an empty portion of the sky, your noise is very weak, right? And therefore, your signal can be weak too, and your signal-to-noise ratio is still okay. But if sun happens to be within anywhere close to the even side beams of your antenna, or if it is in the main beam, then you're looking at the source of the radiation that has temperature 6,000 kelvins or even more. So the power of the noise that comes from the sun is huge. And what happens in those cases, you just have to live with it. And you know, there will be an outage. And we know that it's not a unique situation. If you design microwave links, there is some outage on them. If you design cell sites, there is some outage. If I go in an elevator, the call drops, right? So there's always going to be situations in our systems where we might have an outage. Here, what you need to know is follow the orbit of your satellite, be able to understand when is this going to happen, and then do engineering things, reroute your traffic, use different satellite, or simply just tell to your users there will not be a service within this interval here. Fortunately, the durations are relatively short. I have here around 10 minutes per day. So if you look at it, it's 0.02% of the time over 1 year. That's not great reliability. Remember, in the microwave, I don't know if I covered microwave, but in microwave links we shoot for 4 nines, 5 nines, so less than 0.1%. So you're going to have some significant outage because of this, and you just have to deal with it. All right, so what I'm going to do now is let's go to some examples that I'm trying to do as many examples as I can because your test is coming up. So let me go to a couple of examples to illustrate some of the material that we have. So this is the first one that tells you a little bit about what kind of speeds do you need to achieve to be able to launch. It says calculate the minimum velocity required to launch the satellite into an orbit. Okay, so here's Earth, and here's satellite flying around the orbit, around the Earth. And and this is velocity. This is high school physics problem, but let's just do it anyway. So if you're flying in a given orbit, then what needs to be satisfied here? Well, mv squared over r, which is the centripetal force, needs to be equal to your gravity, which is mu mass of the satellite. This is the mass of the satellite divided by r squared. So this is centripetal force, this is gravity here. And they need to be equal, otherwise either it will move to higher orbit, or the satellite will move to higher orbit, or it would fall down, depending which one of them prevails. So from here, you can see that these two cancels and 1r cancels, and you get that v is equal to square root of mu over r, which is always kind of remarkable results. Tells you that this velocity does not depend on the mass of the satellite. It just depends on how far do you want it to be about the center of the gravity of the Earth. The lowest orbit will have your r equal to the radius of the Earth, which, well, radius of the Earth, let me just correct myself, plus the age minimum. Now, what is age minimum? You want it to be outside of the Earth atmosphere, right? So, for this example here, I say that this is 6,378 78 kilometers, and the Earth or atmosphere, for this kind of calculations, we can say is 200 kilometers. So this gives you a radius of around 6,600 kilometers, give or take. So therefore, the minimum velocity that you need to achieve is the square root of 3.986 times 10 to the 5 kilometers per second squared divided by 66 kilometers. this gives you about 7.7 kilometers per second. That's the number that I would say remember, but that gives you an idea about how fast you need to accelerate the satellite so that it is launched. Okay, so example 2. It says calculate the velocity of a satellite, the speed of a satellite, in a circle that is in a circle geostationary orbit. So calculate the speed of a satellite in geostationary orbit. Is this becoming invisible? Read it.
Another one.
Kilometers.
Okay, so how do we calculate the speed of the satellite in a geostationary orbit? Well, we go back to our
Kilometer cube.
say again.
The Kepler's constant is kilometer cube.
Kilometer cube. Kilometer cube. Kilometer cube and kilometer squared cancels, and then square root gives you this kilometer. So how would you? How do we calculate the speed in a geostationary orbit? We'll go back to the third Kepler's law that tells us, you know, that there is a relationship between the period of the satellite and its semi-major axis. So by knowing that, we can, this is the third Kepler's law that says t squared is equal to 4 pi squared divided by mu times a cube. Here the t is period, a is the semi-major axis of the satellite, ellipse, and the mu is the Kepler's constant. If you're in a geostationary orbit, you know what your period needs to be. Your period needs to be exactly the same as the orbit of the, as the length of the day. So your period needs to be, I have it here wrong. I hope, I'm just going to write it and you check. I'm almost sure it's wrong. So the period, 1 day is 23 hours, 56 minutes, and 4.09 seconds. Right? And for some reason here I have 24 hours. So it might be a typo, or it might be that I just did calculations with the wrong number. Calculator as well. Right. So here, A is going to be mu t squared over 4 pi squared taken cube root. So this becomes 3.986 times 10 to the 5 kilometers cubed over second squared, and then times this guy in seconds is, well, let me just write here, it's 23 times 3600 plus 56 times 60 and plus 4.09, and that divided by 4 pi squared. And take the root from that. So that gives you a, anybody with a calculator that works? Here's mine, just leave it. Nobody?
It's squared, sir. This thing should be squared.
Hmm?
The period should be squared.
What should be squared root period? Here.
Sir, it's gonna be around 40,000?
Yeah, 42,000. But what is it exactly?
42.164 thousand.
42,164 kilometers. So that's the A. The geostationary satellites are in circular orbit, so that's the same as the radius. And then if you look at, you have thing moving around. What is the velocity? Velocity is going to be equal to the 2 pi times A divided by T. I'm going to probably have to do that here and get it. So this becomes 2 pi
Should be around 3, sir.
164 kilometers divided by this same number, 23 times 3600 plus 56, 60 plus 4.09 seconds. And what does this end up being around? 10.
Kilometers per second.
Okay, so you can see the range, right? This is for LEO, and this is for geostationary satellites. All the others are in between in terms of the linear velocities. Okay. Let me do one problem talking about Doppler shift. This is example 3. Consider a LEO satellite in a circular polar orbit with altitude of 1,000 kilometers. The transmit frequency is 2.65 gigahertz. So we have altitude of 1,000 kilometers, and we have that the operating frequency is 2.65 gigahertz. And the question here is, what is the Doppler shift, I guess, experienced by the Earth station? So let me draw the picture so that we know what we're talking about. Here's the Earth, here's the Earth station, and here's the orbit of the satellite. The satellite moves this is the velocity of the satellite. And the question is, what is it that, how do we calculate the maximum Doppler shift here? Well, we have this velocity here can be decomposed into 2 components, right? One is that it is going straight towards the Earth, and one is the perpendicular. The one that we had in that equation was the one that is, that is straight between them, right? And that one is going to be whatever is this guy times the cosine of this angle. And I call that angle here K. So this portion here is radius of the Earth, and this portion here is your altitude. And then I say essentially here that this is the one that matters, so I call that VST. So VST is going to be VS times cosinus cosine of this theta angle. Now the question is, how do we determine that theta, and how do we determine Vs first? The Vs is going to be equal to 2 pi times the radius of the Earth times the plus the altitude divided by the period of the sun. But period, I know from third chapter's law, can be expressed as 4 pi squared times the a, 4 times squared over mu times the a cubed. But a cubed here is 4 pi squared over mu, but a here is RE plus h cubed. Right, so that's from third chapter as well. So if you look at here, I can easily substitute t in here and get everything in terms of the constants and in terms of the radius of the Earth and the altitude of the cell.
So, does that mean the orbit is circular?
Yeah, circular. So if you substitute that, or what I didn't do, I just calculated here. From here, I calculated the period as 63069 seconds. Okay, about less than 2 hours. So once you know the period, then you can substitute the period in here and get that your velocity of the satellite is 2 pi 6378 plus 1,000, and that divided by in kilometers, divided by 63.694 seconds. So that gives you that your velocity is 7.35 kilometers per second, which is along the lines from which we expect. Remember, it has to be somewhat smaller than 7.7 kilometers, and since this is a LEO satellite, it's close to the value. Now, how do we determine this angle theta? Well, we see, let's see here, I can say that VSR is going to be this Vs cosine theta. And I can say that this is Vs times Re over Re plus H. Now I'm just copying this from the notebook. Let's see, why is this the case? Right. Why is this the case? Well, cosine of this angle, this and this is normal, and this, this. Oh, when is the, I kind of drew this in a general case, but when is this velocity largest? When is it largest? When you're just coming, when is the satellite traveling towards the point on Earth in the fastest speed? 30. Not 30. When you're just coming above the horizon, right? Because when you're up here, your velocity is tangential, right? So you're kind of going parallel to the Earth station. But when you're coming up of the horizon, you're actually moving straight towards, or your component towards your Earth station is the largest. So let me redraw this a little bit so that you can see this is the satellite. Let's say this is the Earth station. So that's a tangential plane. So at this point, the satellite is moving the fastest towards the Earth station, and the angle here is 90 degrees. So that helps us calculate what the theta is. There's tangential here. So if you look at this angle here, that's the same. This is normal. This is normal. So it's the same as this angle. theta, theta. And cosine of this angle is this over this. Right? So that's what I have. So when you're coming here, your largest, you have the largest component. This, and as you move here, for example, your component towards the Earth station is 0, right? Because your entire velocity is pi. And what matters when you calculate Doppler shift is the component of the velocity that connects the transfer and receiver, the one that makes them either come closer or move away from each other. So when you substitute the values here, this ends up being 735 kilometers per second, and then times 6378 divided by 6378 plus 1,000. And this gives you 6.854 kilometers per second. So that's the I guess, largest speed of them either approaching one another or when you're at this point moving away from it. Right? At this point, they're kind of getting closer. At this point, they're going away. So this would result in the highest Doppler shift towards the positive, towards the frequency increase, and this would result in the highest Doppler shift towards the frequency decrease. So now your delta F is calculated at VSR, or this velocity here, divided by C over F, or essentially, I have the equation, let me just write it that way. VSR divided by lambda, right? Where lambda can be expressed as C over F, so this becomes VSR over C times F. And in this case, this is 6,354 kilometers kilometers per second. Speed of light is 3 times 10 to the 5 kilometers per second. And then our frequency here is 2.65 gigahertz. So when I plug in these numbers, this results in a Doppler shift of 56.13 kilohertz. Now, that's if you're moving, if you're at this point, this is plus 56.13 kilohertz. And if you're in this point here, this is minus 56.13 kilohertz. So you can think of your spectrum being shifted by 100 kilohertz, from one extreme to the other one. And what needs to happen is your receiver needs to understand that and compensate for this. So your local oscillator needs to also be able to shift and its frequency of operation so that it can be launched in the receiver problem. Okay. That's all I have for today's lecture. Any questions, concerns? Okay, logistically, on Thursday, we're just going to be doing problems. I'm going to be solving the ones that are at the end of the book. You bring your questions. Anything we'll discuss next time. And then next Tuesday, we're going to have the first quiz.